Welcome back. In the previous lesson, we covered the topics of the support vector machine basic concepts. In this lesson, what I'm going to do is go into the actual implementation of a support vector machine, albeit a linear kernel. Before we go into that, I just wanted to show you this useful tools called Orange. And now, especially if you are not familiar with Python or coding, you can probably make use of this to get up to speed really quickly. And it's a very friendly tool. It's built with compatibility with Python, as you can see here, Python scripts here. So I'll start off with file. Okay, so I'm going to choose Iris. There's a few data sets that's available there. So I'm going to just choose Iris. Okay, I'm going to load that, and I'm just going to have a data table to show what we have: the iris, the setosa, the versicolor, as well as the virginica. And then we have the sepal length and width, sepal length, petal length and width as well. You can also visualize it. So it's actually a very powerful tool, very handy, especially if you are not familiar with writing the code or not comfortable with writing the code yourself. And what I'm doing here is just basically plotting a scatter plot. Okay, let me just bring this over, and we're going to use all the data rather than some of the data. Clear all data to data. Okay, and right, so here the axis X is petal width, axis Y is the petal length. This is the part that you probably should be quite familiar with. We've seen this in the previous lesson, whereby you have the setosa here, the versicolor, and also the virginica here. Right, we're leaving that there. What we're going to do next is, right, we're going to run support vector machine. We've already seen this previously. Okay, what we're going to do is that we're going to use the support vector machine, and we're going to make use of the test and score. Okay, so bring the file here, the data here, and also run our support vector machine. And let's see. Right, so just looking at this, we have a tenfold cross-validation and stratify as well. The area under the curve is 1, is a perfect one. The classification is 0.967, so 96%, which is pretty good, especially when you consider that we are just using linear. All right, a linear kernel here. So let me just leave that there in that corner. And if you look at the F1 score, it's pretty good as well. These are the precision as well as the recall score that comes with the support vector machine. So let's just plot it again. So when we actually put a confusion matrix as well as link it to the scatter plot, this is what we get. In terms of the confusion matrix, this is what you have. So there are actually some errors here, these 4 and 1 here. So we'll select those misclassified. So let's have a look at this. Okay, so what we can see really is the fact that it actually struggled with between the versicolor, okay, especially those that's nearby, and virginica. So basically between these, it got confused really. The 1 is this one here, and the 4 is these 4 here. Right, having that as the background, what we're gonna move into is actually the actual implementation of this using Python. Right, we're gonna download the iris dataset again, and we're gonna perform the train test split, and we're gonna run a standard scaler to standardize to scale our data. Again, we're using petal length and width, and we're gonna select that and slice that those two, petal length and width, and store that in X. Again, we converting the string to 0, 1, 2 and store that in Y, and we're basically splitting our data to train and test set. Now, obviously, you can actually do this with the stratified K4 later on as well, but for now, we just want to build our model first. We are giving 80% of our data to actually train the linear SVM, and the random state is stayed at 0. Right, so this first thing is to actually scale our feature with scaling X and fit transform so that we can actually apply SC underscore X to our X test later on for the data that we have not seen. Now we're setting C is equal to 1 right now, and the classifier is the same as the one that we have seen before, and then we're running the fit function with using the X std train, the scaled X, and also Y against Y train. All right, that's really what we actually set aside. As we have covered before, we have a training set and a test set. Okay, so right, moving on to the actual cross-validation score, cross-validation predict, confusion matrix, as well as calculation of precision, recall, and F1. We're just importing these libraries, and we're running the cross-validation within the trained dataset. And what we get in terms of the accuracy is 95%, slightly lower than the orange that we looked at. The so-called standard deviation is 0.05. And we're going to run the train prediction, and using cross-validation of 3, and we have a look at the actual confusion matrix itself. With this, you can see 3 and 3, there are 6 mistakes. Okay, the accuracy, or rather it makes 6 erroneous prediction. When we actually run the precision score, recall score, F1, they're all actually 95%. Right, so having done that, these are all within the actual training set, building our model, running the training set. Now let's have a look at how well does the actual model does perform when we apply this to the test data. The first thing that we want to do is that we are fitting this into the cross-validation, but this is for the predict rather than for the train. Previously we run it on the let's see, we've got cross-validation score. This is for within the training set. Now we're applying it to the predict, and we need to transform the test X test data, and we're feeding Y test as well as applying a cross-validation of 3, 4 cross-validation. And we store our prediction to Y test predict, and let's have a look at the confusion matrix. Right, it's only got 2 errors here. Okay, 2. I think out of let's have a look. 11 plus 13 plus 4. So out of 30, it got 2 wrong. Okay, so 2 divided by 28 gives us 7% of errors, so 93% correct. So if we calculate the precision score, it's 94, recall is 93, and F1 score is 92.9. Now, this is really the actual process flow. How can you actually improve on this? First thing is that you can actually run a stratified K-fold so that the actual class proportion is preserved. That's the first thing. The second thing is that we can tune our model a little bit further. In later on, in the future lesson, in a couple of lessons time, I'm going to show you how to tune it, basically using grid search to actually tune the model so that it actually be trained to be more precise and more correct as well, so find the optimal parameters of C. And for now, this is really the process flow I just want to show you. The first thing is the scale the features, fitting the model, run our cross-validation within the training set before we go and test it out in the test set to see roughly how well the model will perform in unseen data, and it's roughly around 94%, which is pretty reasonable when you actually look at the overall performance between the train and test. They're not too far apart. Right, before we move away from this lesson, and that's pretty much the end of this lesson, what I'd like you to do is actually run the whole process again, except try changing the training set, the training size to 90%, and see whether the actual performance improve or not. And the second thing is vary the C. Instead of 1, change it to 0.01 to see if the overall accuracy improved within the training as well as in the test data set itself. So pause the video now, give that a go. When you come back, I will wrap up the lesson and share with you what we're gonna move into next. Welcome back. I hope you actually tried that out and observed the actual process itself, and whether you've seen any improvement with the tweaking of the training size as well as the C, the hyperparameter C. What we've covered in this lesson really is the actual process flow of implementing a linear SVM, from scaling to fitting to cross-validating within the training set as well as the test data set. When we come back, we're going to look at the polynomial kernel, a slight variation of this, and this is really the power of SVM, is that you can fit in different kind of kernel. We've shown you linear so far. We're going to look at polynomial and a different variation of that in the future video. For now, that's all that we have. Look forward to seeing you in the next video.